So our first question on this exam, and this exam is mostly covering carbonyl chemistry, is for us to predict the products from a series of reactions. Our first reaction is the reaction of an aldehyde with a ketone in the presence of strong base. So this reaction initially looks like it's the correct conditions for an aldol condensation, because we can form an enolate, and the enolate can do nucleophilic attack into the carbonyl. Even better, we have clear choices as to which compound will be the nucleophile and which one will be the electrophile. Our aldehyde, benzaldehyde, has no alpha hydrogens. Therefore, it has to be the electrophile. And that means that the ketone, cyclopropanone, will be our nucleophile. And so we can attempt to remove an alpha proton from cyclopropanone. However, the enolate that would form would be a three-membered ring containing two sp2 carbons. And we've said previously, the double bonds don't really exist very well in three-membered rings. It creates too much ring strain. And so it's extremely likely that due to the ring strain of this three-membered ring, that this enolate would not form at all. And if the enolate doesn't form, then this is not going to react. In part B, we have the addition of hydrazine and potassium hydroxide at high temperature to a carbonyl. This is a Wolff-Kishner reaction. And the result of a Wolff-Kishner reaction is that when dealing with an aldehyde or ketone, that aldehyde or ketone is completely reduced all the way to the hydrocarbon. In part C, we have an ester as our functional group, and we have sodium hydroxide, a base. We know that these conditions will promote hydrolysis. And so what we will end up with is cleavage of the ester bond to form the carboxylic acid as well as an alcohol. The only thing that makes this problem slightly unusual is the fact that the original ester is cyclic, and therefore it's not going to split into two different molecules, but into one molecule with the carboxylic acid at one end and the alcohol at the other end. In part D, we have an ester reacting under basic conditions. This reaction is generally going to be a Claisen condensation. The first thing we have to look for, though, is we have to make sure that our alpha hydrogen, or our alpha carbon, has two hydrogens on it. Remember, if there's not two hydrogens at that position, the reaction won't go forward. But in this case there are, so that's not something we need to worry about. And so we'll get our aldol condensation, which we hopefully remember is just the addition of an enolate in an acyl substitution type reaction. And if we draw one compound as is, because it will end up staying the same, its alpha carbon is what we'll substitute for the acyl group, the methoxy group, on the other carbonyl, and we get that product. Part E is a Grignard addition. And it's a Grignard addition to the ketone. And this cyclopropane ring doesn't actually do anything. But we have two places that this reaction can occur. Remember, nucleophilic addition, if the carbonyl is unsaturated, can happen 1,2 directly at the carbonyl, or 1,4 at the alkene carbon. In this case, though, because the Grignard is an irreversible nucleophile, we only see 1,2 addition. And that's because 1,2 addition always happens first, and we only see 1,4 if the initial 1,2 addition is reversible. In this case, that addition is not reversible, and we see only the 1,2 addition as the product. Part F is just an esterification. So we'll form a new bond between carbonyl of the carboxylic acid and the oxygen of the alcohol. And from there, everything else stays the same. Part G here is an alkylation. Normally in these reactions we have to worry about whether it's going to add the more substituted or the less substituted alpha carbon. That's not a concern here. And the reason that's not a concern is the more substituted carbon here doesn't have any hydrogens on it. So the only place this reaction can occur is over here. With our nucleophile being a methyl group, we'll end up with an addition of an extra methyl group at that carbon and get our product. Part H is an amidation reaction. It's the reaction of an amine plus an acid chloride. But hopefully you recall that this reaction requires that we have at least one hydrogen on the nitrogen to remove. Since there's no hydrogens to remove off the nitrogen, this reaction won't work. Part I, we have the addition of a cuprate. So up above, in part E, when we added a Grignard reagent, that can only add 1,2. If we want to add a carbon nucleophile 1,4, we need to use a different type of reagent, such as a cuprate. The cuprate gives us 1,4 addition of a carbon nucleophile to the carbonyl, and so we get the new ethyl group at this position. And finally, part J is an alkylation onto an alpha carbon. Doesn't matter which side we substitute on, both sides are the same to give us our product.